Section 2.3, the basic limit laws. And so first is the limit laws, then examples, then assumption matters. And that existence of the limit matters in computing limits, basically. So far in 2.1, we gave you ideas on why we want to find limits, an application of it. In 2.2, we gave you a few graphical and numerical approach, but that doesn't work every time. So we have to give you basically methods that you can calculate limits just knowing the rule of the function. And so this is the sort of sections that will eventually help you calculate limits just by knowing the rule. So we start with basic limit laws. And so we need assumptions. Assume that limit as x approaches c of f of x and limit as x approaches c of g of x, each exist. The first law is the identity and constant laws. And that is limit as x approaches c of x equal to c. So what is the function in here? Function is y equal to x. So y equal to x, the limit of y equal to x at any point is going to be, as x approaches any point, is going to be that value of that point. This one is y equal to c, this is y equal to 1. So limit of 1 or is going to be 1 no matter if and this is the constant function 1. This is the constant function 1. As whatever point x that I decide or c that I decide, as x approaches c, the y value is going to approach 1. And here the shape look like this. This was y equal to x, and then as you approach any point c, the y value approaches c as well. There are a whole lot of now the first two laws that we mentioned didn't use f or g, the assumption that we made, but the rest of them are going to make the assumption. So assume that the limit of f and g exists as x approaches c, then limit of their sum exists and is equal to the sum of the limits, either of the limits. So the limit of the sum, limit of f of x plus g of x, is going to be limit of f of x plus limit of g of x. And so this would, the second one, constant multiple law, can be true for f or g, but we're just because we're assuming that both f and g have limit as x approaches c. So limit of the constant times f as x approaches c is going to be the constant times the limit of the f of x as x approaches c. So basically, or the other way we say this is that the constant can come out of the limit. See, the constant basically was in the limit here, then it came out of the limit and multiplied it. And so then product law, if the limit of f of x and limit of g of x both exist as x approaches c, the limit of their product is going to be equal to the product of the limits. These are very simple and very useful for what comes next. So the next law is the quotient law. A quotient law requires one extra assumption beside that f of x and g of x both have limits as x approaches c, and that is the limit of the denominator should be not equal to 0. And so this one is telling us that if both limit exist, then the limit of the quotient is going to be the limit of the numerator divided by limit of the denominator, basically. Next is the power law. What is power law? If n is an integer, limit of x as x approaches, limit of f of x to power n as x approaches c is equal to limit of f of x as x approaches c to power n. That is, n comes out of the limit again and goes to the exponent comes out of the limit and it becomes the exponent outside the. A few examples of basic limit laws to compute the more complicated or more complex expressions. And so this is an expression. Going back in here, I see a bunch of laws that relate a function to another function, or another function to multiple functions, and then I see a couple of laws that actually give you the value, the numerical value for the limits. So the goal is start with a more complicated law and break it down until you arrive at these two, basically. So we start with the more complicated law. Limit x to the third plus 4x squared minus 3, x approaches c. The first law that I'm going to use is, because there are, when I'm looking from outside, I see sums and minuses, so there are a bunch of terms and I want to separate each term. And so to do that, I use the sum law. And so with the sum law, we end up with limit x approaches c of x to the third plus limit x approaches c of 4x squared plus limit as x approaches c of negative 3. And so now the next step, I'm still not there. I see that if I use the exponent law or power law, I can actually end up with this term to be one of these two. So that's what I do. So each term separately, I use another law. And then here, what we're saying is that we take the power outside. So that's the first thing. Then second term, I'm going to use this constant coefficient thing, constant multiple. And so this time 4 comes out, limit x goes to c of x squared. For the last one, I'll also use the constant coefficient, and I get negative 3, limit 1, x goes to c. Now that I'm at this point, the first one actually I know from this rule. I can use that rule in here. So inside the parentheses is just c. So c to power 3. Then the other one, I think I have to do one more rule. What is that? That's the power law. So limit x goes to c to power 2. And this one is already done also. Inside the limit itself, limit of 1 as x approaches c is equal to 1 right there. So we end up with minus 3. And now at this point I have c to the 3 plus 4. Oh, limit of x as x approaches c again is one of those two. It's going to be c squared minus 3. So that's the value of the limits that we got. And I compare that to here, and I see this as basically plugging in c into the function. And so we're trying to build up this concept for you that if the functions are continuous, whatever function continuous is, we're going to talk about that soon, then you can just plug it in. And so this is the section that prepares that for you. And this function is a polynomial. And we just saw all these steps that we took. The similar steps for every polynomial has to be taken. And so you see that all those steps basically bring you down to plugging in the C in here. Now let's do another example. And this is a limit of a quotient function as x approaches C. C is a little higher than it should be, right there. So how do we go about doing this? First, and with what we did with the polynomial, we broke it down. With this one as the quotient is what comes in mind first, and then so what I do is I use the quotient law. So to use the quotient law, now we talked about the fact that we know that each polynomial, the limit of polynomial is just, we can plug in by previous example. We know if we are finding limit of polynomial, we just plug in. So that's what I do, because here when I'm trying to find the limit of the quotient, I have to find the limit of the polynomial first, and limit of the denominator first. And denominator in here is a polynomial. And so if I plug in this polynomial, if I find the limit of x squared plus 5, x goes to c, by plugging in, I get c squared plus 5. Again, this is now that we did the previous part, now we can see this is correct. This is never 0. Why is it never 0? Because c squared is always bigger than or equal to 0, therefore this is always bigger than or equal to 5. And so it's safe to use that law of and so I'm gonna separate things into limits of the top as x approaches c over limit of the bottom. And now going back to what we learned before, I can, because these are polynomials, I can use first the law of sum to separate each term. So basically, if I want to redo everything, I can write it like this. For the top, and write it like that for the bottom. And then do one more law, and then eventually end up with plugging in c for everything. So I end up with c to the 4 plus c squared minus 1 over c squared plus 5. That is, I'm skipping a few steps because I realize that this is a similar process, and I will end up with, if I have a quotient function with a polynomial on top and polynomial in the bottom, then all I need to do is plug in the value that x approaches to get the, basically do direct substitution to get the value of the limit of this more complex function. Let's do one more example. This time it's another quotient function. And the quotient function is limit x squared minus 2x minus 15 over x squared minus 9 as x approaches c. So as we know, for quotient functions, the first thing that comes to your mind is just plug it in, right? But remember, with the last one, we did the testing of the denominator first to be able to do that. So here I'm going to test the denominator first to see if the denominator is going to be ever 0. And so the limit of the denominator is going to be c squared minus 9. And so this one is not always non-zero. Actually, for c equal to plus or minus 3, this limit is we cannot use the power law that we used over here to evaluate the function. And so actually at one of these c values, still at one of these c's, actually the function will have a limit, but we cannot use the basic limit laws to find that limit, and that's for something for the next section that we discuss. So if c is not equal to plus or minus 3, I can just plug in and get c squared minus 2c minus 15 over c squared minus 9. And then we go back and we find that for actually one of the c values, there is also for c equal to plus 3, there is a limit. I'm sorry, for c equal to negative 3, there is a limit. And how do I know this? If I if I plug in negative 3 in here, I will arrive at 0 and 0. And in this specific case, this still has a limits, and basically it's something that there's a hole in the graph of the function, very much like the problem that we did before. But explaining all that, it comes in the next section. So right now we're just saying, according to the basic limit laws, this is true if c is neither 3 or minus 3. I click here question 2. First, before doing the iClicker question, it turns out now that we basically talked about a few polynomial functions and a few functions that we had a lot of information about. Now let's talk about functions that we have only local information about. And so here is, you see that this part is given. These information is the local information, and it's all the information that I have about the function. And we're trying to use that information to calculate this limit down here. Again, as we did before, I need to break down longer expressions. So I really need to use the law of limits to break down the expressions into something that carries information, as limits that carry numerical information. And so how do I do that? First thing first, it's this consists of two terms. So what I do is I divide it into two limits. I write it as sum of two limits, So then I use, so this was the law of sum. Then for each term, I use the law of coefficient. So this one comes out, and then that one comes out, and I'm going to use a negative sign because plus minus is negative. And now at this point, I can go back and find information. And so I see that limit of g of x as x approaches -1, which is one of the limits that I need, is right here. Also, I see limit of f of x as x approaches -1 is right there. So I can replace those two. I can replace that and this by its values. This is -2. The other one is 3. So I end up with 2 times 3 minus 3 times -2, which is 6 plus 6 is 12. And that's the limit of the longer expression. So in the next example is another quotient rule. And so what we need to do first is to make sure that limit of the denominator is non-zero. So let's figure out the limit of the denominator as x approaches 2. And so that would be, according to the exponent law, it will look like this. And so I have to go back and find limit of f of x as f approaches 2, and that's the one. And so in here I have a -1, so -1 to power 2, and that is 1. So the denominator is not 0. I can basically find this as limit of the numerator divided by limit of the denominator. I have calculated the limits of denominator. I don't want to do it twice, but now I have to use a product rule for the numerator. And so a product rule for the numerator, I'm putting the value of the limit of the denominator down here. Limit product law gives me this. And so at this point, I know the first one of these, and that's according to the basic laws of limits, and that would be 2. And 1, I don't have to write it down. According to the iClicker part, we're saying that g of x to power 1/2, if the limit of g of x as it approaches -1, and as it approaches 2, if it's positive, if the limit of inside is positive, then I can actually take the square root outside the limit. So let's see, is limit of g of x as x approaches 2 is equal to 4, therefore we're safe. And so I'm going to use as limit as x approaches 2 of g of x and square root. And now I write 2 square root of, this one is 4 according to that, and it's going to be 4. One of those other limits that, and this is example 4, part 3, one of those limits that we are not able to do with the basic laws, but in the follow-up sections we are able to do, is this limit. So it's a quotient, but the top part is a composition function. So I still cannot do that with the rules that I use, but we'll see in the follow-up section that we're able to do that. So I'm taking a range check for this one. It's a range check, and I will explain this and at the end of section 2.4 basically. Let's do